Hi, in this video we're going to talk about a very important tool when we want to analyze circuits that like the RC circuit, which is called the transfer function. So when we have a circuit like this, the first thing we do usually is we just substitute our elements by our impedances. So instead of C, I'm going to put here J1 over J omega C. Now, the transfer function of any system is defined as the output over the input. Now, in this case, we're interested in the output voltage, and we have an input voltage here. So our transfer function, which is represented as H of J omega, is our output voltage over our input voltage. And now, because we're going to be interested in what happens in many frequencies, so we're not going to put a particular frequency, we're going to leave that as omega. And we're going to calculate now what the output voltage is with the circuit as it is written right now. So, the output voltage would be then the voltage divider, like we saw in the previous example, is the input voltage times the impedance of the capacitor over the sum of both. So, the output voltage is going to be this one times ZC, which is 1 over J omega C over R plus J omega C. And now we just rearrange so that things look a bit nicer. I have here, sorry, this is wrong. Like this. So I have two quotients there, so we want to get rid of that. So that gives me our C J omega plus 1. And here I have VI over J omega C. So that one cancels out with that one. I end up with my transfer function, which is the output over the input. So I just bring this one over here, is output over the input is equals 1 over RC J omega plus 1. Now, usually we want to leave the J omega alone, so I'm going to take the RC out, and my transfer function will look like this, 1 over RC times J omega plus 1 over RC. And then I just bring this one up. So my transfer function is 1 over RC over J omega plus 1 over RC. So that is my transfer function. And this transfer function is very useful to analyze other properties of the circuit, like for instance we did before, the step function, the step response. In this case, this is very useful to analyze what we call the frequency response, which is what happens to my circuit when I put many frequencies in it. Note one very interesting thing here. We have here 1 over RC. When we were looking at the step response, we had that tau equals RC, and that was in seconds. And here we have the inverse of that. So this is actually a frequency there. And it is a very important point here, because here we always have in transfer functions is a quotient of something. We have a nominator and a denominator. And in the denominator, it's a very important thing here, because the roots of the denominator of the transfer function give me what's called the poles of the system. And the poles are the points where my transfer function goes to infinity. So here, my pole will be 1 over RC. So if I substitute omega by 1 over RC, everything goes to 0. I mean, the denominator goes to 0 and my transfer function goes to infinity. And this is a very important thing. We will look into that in the next video. So the important thing of this video is how to obtain the transfer function of any circuit that has capacitors or inductors on it. We just put the impedance, and using Kirchhoff or Ohm's law or whatever other analysis method we want, we calculate the output voltage over the input voltage and rearrange so that at the end we have something that looks like this, where we have a numerator and a denominator, and in the denominator we have our j omega term alone. And that's our transfer function. In the next video, we're going to see everything that we can find out about this circuit just by analyzing this transfer function. So, thanks for watching.